Hi, welcome to today's lesson on systems of linear equations that are special cases. Okay, we have solved them so far using substitution, elimination, graphing, elimination when we needed to multiply first. We've done all the possible ways to find a solution. Now we're going to kind of find the ones that don't have a solution. And there's really only two types that won't have a solution. Okay, or they have too many solutions. We'll talk about that. So as we know, a solution to a system of linear equations is the spot where they meet. Well, we saw a type of line the other day where they don't meet. So what happens if I have a graph and I'm trying to find where do these two lines meet? Now, I didn't draw them perfectly, but you get the idea that these lines are parallel. They aren't ever going to meet. So how do I solve that? Well, I solve it the same way. I just need to be able to accurately interpret the results. Okay, so there is absolutely a time when there's no solution, and no solution is going to be our answer. You know, because that's what they're saying. They say solve, they say find the solution. They're saying where do these two lines meet, and your answer is they don't, because that's what parallel lines do. They don't meet. Now, how does that look? We're going to see that in just a second. The other one's a little harder to really wrap your brain around. Okay, and it's, let me try it with some color here. I draw my little graph, and then I draw a line. And then I say, where does this line intersect with the line I'm about to draw? Now, obviously, I didn't draw it perfectly, but hopefully you can see that it kind of overlapped. Okay, that it literally is the same line twice. That would come up as infinite solutions because it's the same line. It's like, where do these two lines touch? Everywhere that they exist, they touch because they're the same line. And again, we're going to see how does that manifest itself when we're actually solving using one of our methods. We could be using graphing, we could be using substitution, we could be using elimination. How does it look when we do this? In fact, we're really going to focus on, it doesn't even matter. Elimination and substitution look the same. Graphically, you have to understand it. You have to just look. You saw what I just drew. If they look parallel and they tell you they're parallel, then they're not going to touch. No solution. If they draw one line, what looks like one line, but they tell you it's really two, they're telling you, hey, it's the same line overlapping, the second line overlaps the first, and the number of solutions is infinite solutions. Okay? And we'll see what that looks like when we solve it using either elimination or substitution. Probably elimination, because that's still my favorite. So, how does that look? Again, we just get the question to solve. And we get two equations, 3x plus 2y equals 10, 3x plus 2y equals 2. And you can almost see right away that something looks a little weird because they both have 3x, they both have 2y, and then they have different numbers afterward. Well, let's not try to read too much into it. Let's go right to the solving. I would line them up. Well, they're already lined up. They're already both in standard form, so I'm ready to go. They have a common coefficient, the 3 here and the 2 here, so either one. So I decide to subtract because they have that common coefficient. And 3x minus 3x is 0. 2y minus 2y is, well, 0. And 10 minus 2 is 8. So I end up with this. I end up with a statement that says 0 equals 8. Well, that's not even true. This is what we call a false statement. And I mean, it's sort of obvious that it's false. But what does that mean to us when we see that it's a false statement? It means that there is no solution. That's what it means. A false statement means no solution. Now let me expand on that just a little bit here. If we were to take that first equation and rewrite it in slope-intercept form, so I'm going to subtract 3x from both sides. So 2y equals negative 3x plus 10. And then divide through by 2. I would get y equals negative 3 halves x plus 5. Now I don't want to graph it, but I know exactly what it looks like. It has a negative 3.5 slope, which means it goes down 3 and 2 to the right, and it starts at 5 on the y-axis. Now if I do the exact same thing with the other equation, so I subtract that 3x, so 2y equals negative 3x plus 2, and divide by 2, I'm going to get y equals negative 3/2 x plus 1. Hey, they have the same slope. Well, that was from a few weeks ago, but we saw a lesson that said if they have the same slope, it means they're parallel. Because they have different y-intercepts. They cross the y-axis at different spots, which means one's going to start at 5, one's going to start at 1, and then they're both going to go down 3 and over 2, down 3 and over 2. And they're never going to hit each other because they're going to follow that same pattern forever. Okay? So when we get this situation, we need to understand, what does that represent? That means there is no solution. That means the two lines are parallel, and the fact that we get a false statement means that no matter what x and y ever are, it'll never work. Okay? And that's where the never no solution kicks in and really reveals itself. Now we could have done this using substitution. It would have come out the same way. You can see, because I have solved these for y. If I put them equal to each other, the first thing that would happen is I would add those 3/2 x's out of there, and I would get 5 equals 1, another totally untrue statement, and therefore, again, it would tell me that there's no solution, that these two lines are parallel. Okay? So it doesn't matter what method you use. If you see that they have the same slope, you know they're parallel. If you have two lines, if they have different y-intercepts and they have the same slope, they're parallel. If when you solve them you get a false statement, they're parallel and they have no solution. And I'm going to write that out at the end here. So I'll just have it for you. The other alternative would be something that looks like this. X minus 2y equals negative 4, and y equals 1/2 x plus 2. Now here I have one equation written in standard form and one written in slope-intercept form. Now I still have a lot of flexibility on how I can go ahead and solve this. I could turn this into standard form pretty quickly, and then I might have to do something so they have a common coefficient. Or it's already got y isolated. I could just do substitution, substitute it in. Okay? Or I could turn this one into something that could be graphed, because this is obviously pretty easy to graph. Whole number, nice fraction for the slope. Okay? How you want to do it, up to you. I'm going to use substitution because this is already sort of set up for that. So I'm going to say x minus 2, and then I'm going to replace y with 1/2 x plus 2. And now I'm going to solve for x. I'm going to multiply. So negative 2 times 1/2 would be negative 1. Negative 2 times positive 2 would be negative 4. Combine like terms. 1x minus 1x would be 0, and I'm left with, hey, what am I left with? I'm left with negative 4 equals negative 4. A true statement. Well, what does that mean? Well, a false statement meant no solution, so a true statement means infinite solutions. Symbol for infinity. Infinite solutions, because really this is the same equation, just written, one is written in standard form, one's written in slope-intercept, but they're really the same equation. If I made tables, they would have the same values. If I put them on the graph, they would overlap. They're the same exact set of values, just written in different forms. Again, going back all the way back to fractions like we did a while ago, it's like, what symbol do I need to put between these two fractions? All the numbers are different, but we all know that 1/2 equals 2/4. I know that x minus 2y equals negative 4 is also the equation y equals 1/2 x plus 2. They are the same representation of points. They all, if I put them on a graph, they'll overlap. And when I solve it, I get a true statement with no variable. That's the key. A true statement with no variable. Okay, if I get x equals something, then I just plug that into the next equation, and then there's going to be one solution. This is going to be either no solutions, because I get a false statement with no variable, or an infinite number of solutions, because I get a true statement with no variables. So let's write that down, and then we're gonna be done here. So if after using any method you end up with no variable and a false statement, then no solution. If you end with no variable and a true statement, then infinite solutions. So this would be like 4 equals 5, and this would be like 4 equals 4. Okay? Here, no matter what the variables were, it'll never work. Here, no matter what the variables were, it'll always work. And those are the two possibilities for the special cases. So there's now 3 possibilities. One solution, that's what we've been finding all along up till now. No solution, they're parallel. Infinite solutions, they overlap. They're really the same equation, just written in different formats. So solve it and figure out which one you have. All right? And that brings us to the end of systems of linear equations. It brings us to the end of this semester, and all things being equal, hopefully the end of 2020. See ya.